hard academic, in my opinion. I have learned a lot of things about writing, for example, through ULA. He works in the unit of subject matter education with a specialization in mathematics education. He also, another fact about ULA is that he has a surf deck company. That's, I think, is cool. He designs the decks, and it's not the name decks, right?
The board.
Board. Thank you. The
Windsurfing
board. Windsurfing boards, and he has this company for that. I'm talking more about surfing, I know, but he's in the intersection of surfing and mathematics education, and so I think it's cool, right? And I'm very happy that he accepted to cross the Atlantic and come here to talk with us. Thank you very much. That he's dressed up, so taking very seriously this thing. Okay, Ula, the floor is yours. Thank you for coming.
Thank you so much, Mario, and the whole institution for inviting me, and the conference for inviting me. So I will talk about this. This was my title: Implementing Content-Based Mathematics Teaching Innovation at Scale. So that was my title. And I will actually not so much talk about the research in a sense, because and I can also say, when I say we, it's usually me and Linda, but we are a few more in this project. But what we are interested in is actually having an effect on the education, on the people, the pupils learning mathematics. So we prefer to have a big effect and make a kind of a dent somewhere than to do a lot of good research. So I will not speak so much about the methods and so on, but I can also say that in this project that I will talk about, we are two other people that do the statistical work mostly. I hope somebody should mention this, because this is like a little joke I made. The black screen. and actually it's not completely. There is a little bit of text here, which it's even harder to see than I planned. But this is a joke because some of my slides, they will be a little complicated, so they are more like metaphors or stuff that I will point to. So you made my joke work well here. So this is not it's an intended thing. So the thing that the students don't learn as much mathematics as we would like, it's not just, it's a very important thing, at least in Sweden. We know that quite well, because we have a system. So in practice, you need to pass to the upper secondary school to have a chance in society, let's say. So it's quite hard to get a job and anything if you don't. And we actually have a quite tough rate of passing the grade 9 so that you can start a regular program on the upper secondary. So 16% roughly of the pupils, they are not allowed to start when they're like friends at the same age start. So they have to spend some extra years, and some never really go through. And this is very bad for them. And actually mathematics is the subject that really makes this happen. So it's a big problem. And actually, the failing in mathematics, which starts quite early in school, it has been shown to lead to a lot of psychological problems, actually. And we even have a word. It's called like home sitters, people that stop going to school. And mathematics is the first problem usually. It starts in mathematics and it spreads to the other subjects and to your whole attitude towards schooling. And we decided that we need this much schooling. So it's an obligatory thing to go to school, and everybody has to study mathematics, so it's not an option. And this kind of way of looking at the whole school system, it has guided, at least recently, my whole view on what you should focus on as a researcher and developer. So before I wrote these books about, this is mathematics, it's very exciting and so on. But now we cannot change our outset on this. So because which mathematics should we teach? and which should we focus on as researchers? Well, you can do whatever you want, but we focus on the mathematics that is the best to learn more mathematics, so that you can function the best possible that you can according to your sort of genes and whatever in school. So and this is actually quite a creative turn to think about the mathematics. It's to think about it in a kind of a generative way. So we teach the math that makes it easier to learn more math, and that's it. So that's one way of thinking about it. And this is kind of what lies behind. So now actually we have a real problem. So now it stopped working again. So now we have the same. So my computer recognizes this one. It's just that this one doesn't show. Ja. En gång till. Okay, so it was. Yeah, they probably restarted that one because I had this black thing. So that was a planned thing, the black screen. So I shouldn't. I went too far with this. So I can still talk, and then it will probably sort it out. So it worked before. So if you just started and do the same thing like before. So anyway, I will talk about a project that is called Algebra Monday. So this is our solution to the problem I talked about in a way. And this runs now with 5 municipalities. So to do stuff at scale, we're interested in scale, you have to kind of know your school system. And in Sweden, it's usually the municipalities, like a city or some area that runs the school. But we also have like free schools that are outside of this system in a way. And they are organized in a particular way. But as you will see, even though they formally look kind of the same, they work in different ways. So if you're going to do stuff at scale, you have to understand this system of the municipalities. So, I don't think the problem is at this end, it's at that end. So and now this project, it runs with I think it will maybe scale up to 500 or maybe up to 1,000 teachers. So it's pretty big. So I think it's reasonable to call it an implementation project in that sense. And so because we are interested in scaling up to at least this scale, which isn't really very big in a sense. That means it might it's just a few % of the teachers in the whole of Sweden. So we might have like 100,000 teachers, I don't know. So therefore it can't scale to the national level. And I will come back to what you would perhaps need to do to scale it further, and why we can't scale it more than we scale it already, or already scaling it. So, but already at this scale, it means that in some municipalities, all the teachers from grade 0, I mean the 6-year-olds, so we have like a grade before the school, let's say, to 9th grade, all teachers will be involved eventually. And this means that we will involve teachers that did not choose this themselves. So this is a very important issue in scaling, because when you recruit teachers yourself, you can get very good teachers. They are interested in working with you. But if you want to push it onto people, you need to have some organization to handle that, and that's difficult in itself. So that's the scaling. So, So now there will maybe be some slides. So that slide I'm talking to, it's not very important slides really. So this is the plan of the talk. So I will start to talk about Algebra Monday in terms of how it started. Why did we invent this? And then I will go into the background. So what did we actually, like me and Linda, what did we know before we started, and what did we build this on? What kind of knowledge? And this will concern some other implementation projects and some theory, let's say. And then I will go on to the content, the actual algebra. And I heard yesterday that there were some people interested in arithmetics and stuff and so on. So they might want to look at the content. And then I will discuss the collaborative setup that we have with the municipalities and some conclusions in the end. So this is it. So at some point there will be some important slide, but I hope they will get move forward. So how did this start then? Okay, it's that's okay. Yeah. So I don't know. I think that they don't just get this one to. Okay, so you see a little bit. Yeah, so you have to just use your binoculars. Did you bring them or not? And I see mine. So how did it start? So this is, let's say, so yeah. So this was actually started by 2 teachers in one municipality. So they are upper secondary teachers. So they have been running this test for many, many years. I mean, one of them, she was actually a colleague when I was taking the teacher education. So she's, I mean, this was in the 90s, and I didn't really meet her in between. And the other teacher was, he was collaborating with us in another research project. So they have been seeing this declining trend for a long, long time, and it got kind of worse and worse and worse. And this is kind of how it looks in Sweden generally. You don't really see it on all the statistics, but it depends a little bit. But generally the results are going down, despite that we spend a lot of money and have a really resourceful school system. It's a segregated system, let's say, but still kind of lots of resources. So then they simply contacted me and Linda because we had some talk or something that they saw. So because of some comments on Facebook or whatever it was, they contacted us. And we started to plan for what could you actually do? So what should you do? And some of the projects I have been running before, they are very complicated things. You know, so we ask a lot of the teachers to change some very fundamental aspects of their teaching. So now kind of we thought, okay, what is the lowest hanging fruit there is? Really. So what should we do if we, let's say like this, instead of thinking about as a researcher, what would I prefer? What would be some idealistic idea? So if you would gamble on it, you put like 10,000 of your own money. Will this actually make the students learn more if I do it? So I think this is actually a very good way to take a decision. you like. It's like a bet with your own money. So then we decided on this kind of there's some basic things, you know, and we so this is the low hanging fruit. So we wanted to see if yeah, so here. Okay, you will have to look here. Yeah. Okay, now I remember what to say. Yeah, exactly. It's a little bit harder when you don't have the when it's technical things. Yeah. So we started to plan with them. So and we really thought that this algebra and this kind of the symbolic aspects of the math, this is what in the long run will help because this is usually what actually becomes the problems for the students eventually. So typically they go it's pretty easy in the first grades. And then it becomes harder and harder, and then more and more, fail. And it's usually not because some problem in geometry or something. It's because of the basic math, which we formulate as algebra and pre-algebra and early algebra and all of that. So that was one of the decisions. So let's just attack that. And the other decision was let's do it in a minimally intrusive way for the teachers. So that comes to this Algebra Monday. It actually means that you just do specific things on Mondays with us. Otherwise, you have your completely normal teaching. So we take like a day. So this is as you will understand later, it's still kind of intrusive, because in the end it's kind of hard for the teachers, but this is still quite minimal if you want to do something really advanced. And then we also understood from our other earlier projects that you really need to work with the whole municipality. We can't just recruit teachers individually or even schools. So you need to build an organization from above. And I will talk about how that can be done also. So, and we have a few, so now I'm in this background thing. So what did we know before we started? So the name Algebra Monday actually come from Linda's teaching. She taught in prison education for 15 years. And she eventually she developed a way of doing this. So she had the Algebra Monday where she only did basic stuff. And she mixed all the students. So they were taking different courses, from like, secondary education to upper secondary and different courses in upper secondary. She just mixed them and taught them all the same things still. So she, and she had this algebra thing on Monday, and then so for Wednesdays she had like, I don't know, so problem solving, and and some conceptual stuff, new mathematics that were introduced on one day. So it's a kind of smart separation, I think. So we knew that this worked, and actually, so now you won't see this, but here is well, okay, that one, it's stuck now in some old, so it's getting worse. So, yeah, now you see. So this was Linda's teaching, and yeah, like this maybe. I don't know how they. Oh yeah, so they are kind of doing it for me. So are you using the other presentation now, or? Okay. So the next then. Yeah. So this actually comes, some of the stuff she did was that she was at the conference and listened to Uffe presenting actually work he did with Bogensnis. So this is a detection test, some typical tasks from a detection test. So she started in 2014, right after seeing this, to just take 5 tasks from this test and I just teach these tasks more or less. And after a while, she sort of realized the underlying structure, because the problem with these tasks is not that they can't solve these tasks. There is some underlying problem. So when Linda talks about her teaching, she says that I want to compactify the mathematics so that you can do more things with less knowledge, let's say. So when this leads to this algebraic and these structural ideas. So you have to find where is the most basic way of knowing mathematics so that you can solve the maximum amount of practical problems, let's say, or problems. So that was kind of one of the backgrounds. And then is this one. So the next. Yeah. So this is a big thing I did with some colleagues at the National Center for Mathematics Education. So this was actually also presented the first time in 2014, but we started already in 2010. So we designed teaching in arithmetics and kind of early algebra for the early grades. First in this preschool class, and we did it, very thoroughly with randomized controlled trials and stuff. And then we developed this for grades 1 to 3. And we got in contact with municipalities. So we started this with 5 municipalities, and then 5 more, and then 5 more in a complicated system, let's say. Oh, now you don't see anything. It's on another screen. But this was based on a very disruptive way for the teachers to organize their teaching. So we had a very particular design that went over 3 lessons. So every lesson had a different social role between the teachers and the students, and it was very much a discussion-based teaching, let's say, very, very student-oriented. So that was kind of difficult for the teachers. So we wrote this very detailed teacher guide that describes pretty much everything. Exactly what words you were going to use, and then we designed this system with the municipalities to sort of get them to do this. And now I would really like the images. So yeah, maybe this one. Okay. so you won't see here, but oh, now it's, well, I don't know. Is this my? It can't really be my. Oh yeah. But it runs through their system. So none of the animations will work. So actually, I don't know. If it's even better. Yeah, it's better. Yeah. So what we did, we worked together with an organization for municipalities, and we designed like a way for the municipalities to organize this project inside and within and between municipalities. So in the bottom here you see that we sort of designed the kind of groups that the municipalities had to be able to work with us. So they had to form a group with some principals, some teachers, the whole school leadership, and so on. And they had to come to a certain amount of meetings and so on. So, and then they had to form this. They had to educate these pilot teachers or facilitators during a certain amount of time under our guidance. And then these facilitators helped. They formed this collegial group, so they have to provide 1 hour a week where all the teachers could meet, and this was usually like all the teachers in the whole municipality. So this is kind of a complex thing. But still, we didn't have so much. I mean, sometimes we visited the municipalities, and sometimes we had these big conferences where all them came. And it's also kind of, because we did it first with 5, and then with 5, and there was even some kind of educative features between these kind of rounds, you know. So you can take the next one. So this is like a scheme of it's a time frame of this. So it goes over several years, and in the middle you see everything that's happening to this group of 5 that was in the middle. And sometimes they meet the previous group, you know, and sort of learn from them. And then after a while, when they sort of did it for a few years, they are trying to educate other municipalities in this. So that it's kind of ambitious, let's say. But still, I mean, and there are, of course, teachers that love this, and it works really well somewhere, but it also fails somewhere. And to remind, I mean, this is a very strong material component, as Prediger and those researchers say. So it's this teacher guide. So they have to use this guide. The teachers are, you know, working together, understanding what to do the next week and the next week together with their facilitator, and then they do it, come back, give feedback to themselves, let's say. How did it go for you? And there's also this booklet that sort of guides these meetings. So strong material component, kind of a not so strong facilitator component, because these facilitators, they were usually not really educated for a very long time. They maybe had like 5 meetings with us and so on. And then the structure, as I saw, the sort of systemic structure was pretty strong. But we, as researchers and developers, we lost track of this a little bit. And this was before the sort of digital era, I would say. Because now I would do this completely differently. So at that point, we had to, because no teacher would ever touch like a Zoom or, you know, Teams. And the pandemic came in the middle of this also. So therefore we had to go there, you know, so a lot of work. So in some municipalities it deteriorated a little bit, but some are still scaling up, and I think we still have like maybe 800 teachers or something doing it. So what we learned, so we learned that even though these teacher groups works pretty well, they can easily break down. And it's enough with sort of one teacher that sort of starts to resist. Then there will be a very negative trend in this group. And, you know, the principles will be exchanged. So unless there is a really good system with all the principals meeting every week or every other week and always discussing this thing, then it will sort of, some schools will stop doing it because they change principal and he wants to do something else, or she. And some of the things that we asked the teachers to do regarding the actual teaching, it was very difficult for them. And some loved it and some did it very well and so on. So it was hard work. And usually it took even for the best teachers, it took like half a year until you sort of got the hang of it. And that's quite hard to sort of fight for half a year with your students. but you know, still it works quite well. But then also that, yeah, so this is pretty much what we learn. Yeah, exactly. So when we have done a lot of video studies of this, so, and we see a lot of adaptations to our model, and they are usually not so fruitful. So they sort of take away some important stuff and replace it with some bad stuff. We did see some excellent additions that if I would do it again, I would take this really excellent stuff and put it into the whole design. So some used collaborative teaching in a very creative way. So they managed to have these wonderful discussions, you know, and probably many of them, but not everybody. So it was difficult. And then we have another project, and this is about this is also like a teaching model. It was started in a much smaller scale. So this concerns, let's say, I mean, you probably want your students to write nice solutions to your problems. So you say you must write a good solution, but the students never want to do it. They just write the answer. So this is about this, you know, teaching formal written communication, teaching the students to write, you know, really nice and structured written stuff. So I won't tell you about how the model for this works, but this was started in small scale, but already when we started it, we had the idea of we want this to be scalable. And this is actually something important, because when I look at lots of mathematics education research, there are some very nice things going on, but I can see right away, this will never be scalable, because it's too much involvement from the researcher, for example. And what is created could never really be transferred to a facilitator. So if you want to design for scaling, you have to start right away at your actual experimentation stage at the small scale to sort of think about how would the scaling look. So we did this. So this eventually we did scale this up to in one municipality. And this is done with collegial groups also. And now we had learned the digital things because this was after the pandemic. So with this municipality, we developed a structure for how teachers can work together and share their student work really quickly and easily. So they have this, they sort of developed this way. Because if you're going to have collegial discussions with your teachers, if they don't share student work, nothing will happen. So you must always have them share the student work. So they can't just talk, because some will then say, "Oh, it was wonderful," you know, but it was a catastrophe, you know. But if you share, you can't really lie with your students' work. So that's important. So here we learned that. Okay, next. Yeah. So we learned that this kind of idea of designing for scaling, it kind of works. At least it worked in this case. And we learned about the digital collaboration structure. And also, this was actually quite easy to motivate the teachers to do, because they all had these students that didn't write this solution. They asked them, but they didn't do it. You know, they refused. So we offered, well, we have a thing that we know will get your students to do this. And then it was easy for us to motivate them. And it's so much easier to do things if the teachers themselves are motivated. So sometimes you have to do stuff that the teachers don't want to do, but it's good for still. That's hard. That's a hard problem. And then the final thing about this, what we knew before we started, it's so, okay, yeah, of course. So this was supposed to come in some order. But this was from a project that Uffe was leading, which was more like a research on implementation. So it looked into international implementation projects in different ways. And we did a review. I was a little bit involved. So we did a review and so on. And from this we learned that actually this content-based implementations are a little bit easier to do than, let's say, problem solving. Because it's easier to motivate the teachers when it comes to content. And also we learned that, I mean, this four things: the organization, the innovation, the external environment, and the teacher. It comes from Coburn, who actually built it on some other stuff. So this is a way to understand how this sort of components of an implementation project. And I mean, the way we think about it now, it is that there is some tension between the innovation itself, the thing, or whatever, the product, you can almost say, that you want to sell, in some metaphor. So there's some tension between that and the teachers, and it can be formulated partly in this kind of motivation structure I talked about, and partly in how much of the teacher's routines will you have to break, and how many of the old routines will kind of disturb what you want to do with them. So we stopped talking about beliefs and that sort of things. So we don't think that matters a whole lot. So it's much, if you want to understand the complexity of your innovation, you should understand the routine structure of the teachers you want to work with, and see which ones will I need to break, and which ones will be disturbing, and which ones doesn't matter. So this is an analysis, I think. If you should go for scaling, you kind of must do this analysis at some point, because otherwise you don't understand the complexity. But there is also something about the relation between the external environment. That's sort of the stuff you can't really do something about. Perhaps, for example, you have national tests or something. That's typical. Or parents can be external environment. And if your innovation, the thing you get the teachers to do, sort of disturb or goes against this, it will be very difficult in the long run. It might work for a while. And this is very well established, in particular in the American context with the reform teaching, and in many other places. So in a sense then, so when you're building your organization, also the project organization, so here the organization is typically the school. So it's the organization you kind of work with, but you also have a project organization. And the more complex your idea or your innovation is, the more of the organization you need to take into the project. So you need to own it. So you have to sort of own some parts of these municipalities and have them work with you. And this is why I talk about this kind of scaffoldings that I showed you. So you need to construct some kind of groups within the municipalities that deal with this together with you. Let's say, okay, so some theory also. So we can go to, okay, we can take this one. So now there will be, next one. So this will be, this will be kind of difficult because there are many slides I should click through quickly. So algebra. This is a kind of some questions for it in a test we did. I don't know, can you read them like this? Okay. So these are 6 different questions. So the first one, what is A5 divided by A5? And you know what it is 1. And then there is something about simplifying fractions. I mean, 4 fractions where only 1 can be simplified. So which one? Or which of these? And then there's almost the same, but it has some pi's and some x or a's and b's and stuff. So it's not just numbers. And then it's something about also simplifying, like an algebraic expression. And then there is like a thing where you can't really simplify in the same way. So you can't use the standard rule, let's say, in this cubed 31. And then a more complex, more difficult simplifying question. So these are very different tasks for the students, completely different. And the first one, it's actually, which one do you think is the easiest? This is for grade 8, let's say. Yeah, actually it's 10 is easier, in fact. So it's the easiest one. So and we did the statistics on this, so I can actually show you. If you go forward to, let's see, you can click through a lot of them, because these are just enlargement. So if you go to this is like graphical. More. One more. Okay. So this is like a way of understanding difficulty. So it's a statistical thing from item response theory. So the difficulty is on the y-axis. And the one that's up like 7, that's extremely difficult. So it's like 100 times more difficult, let's say, or something. And so you see the second one was the easiest, and then they kind of scale upwards towards more and more difficult, but one was much more hard. And this is, of course, because these tasks are very different. Otherwise, they would be the difficult level would be more similar. Our hypothesis is that when the students have done this Algebra Monday, these will look like the same task to them. And it's because everybody can, all of them except the one with a -1 and so on, can be handled by a divided by a equals 1. So a thing divided by the same thing is always 1. So it's an algebraic rule. So all of these tasks can be treated with the exact only one way of thinking, which handles all this. So we think that our students, then this graph will look kind of more flat, at least these 6 tasks, and we have some system of such tasks in our tests. So that are now very different, we hope they will be more like similar. And you can go to the next one. Okay, yeah. So this is another way of looking. This is from a Swedish researcher. I was at her seminar of her the other week. So this is like linear equations. So this is based on a test she did, but she also did interviews. And this is like a typical way. This is very typical. This is upper secondary, so grade 1. These are 16, 17-year-olds. They have been to school and had math every day for 10 years at this point. So he could solve the first. 3x equals 12. So he divided by 3. And he could do it algebraically, let's say. And he could do the next one with decimals. So then you can kind of think, okay, he knows the drill. But he couldn't do the last one. So and she has, multitudes of these, and the whole research is full of this kind of research. So we know a lot about these kind of errors. And why? He had a calculator, so it's not that. So the calculators were allowed. So, but the problem was he wanted to remove the 0 from the 0 points. So then the whole how was he actually thinking about the earlier ones? What's going on in the head? If you want to remove the 0 when you come, so probably he knows the first one because he can connect it to some concrete thing, and the other one he can just imagine that the a and the b, they are like whole numbers, and then he kind of imagined that the 0.3, that's also like whole numbers. He imagines it works like whole numbers. But then the last one, the 0, kind of disturbs this generalization, this very bad type of generalization. So this is in the secondary education. So if you want to treat this person or the class or the school where everybody almost is doing like this, you have to do some bad things actually, because it's too late. You can't fix it. There's like a big rift between what you would actually need to know for this to be like automatic. So this has to start, in grade 1, I think, or actually, Yeah, so I have a lot of time, but also a lot of slides, if I can get them to. So let's go further. Yeah, maybe this. So this is kind of, so how do we want to do this? So this is, we want to we see these problems occurring quite late. Maybe we see them a little earlier also. But how does the progression look? Because when we look at textbooks and stuff in Sweden and kind of internationally, at least in many countries, for us, it looks very bad because you do stuff that we know will lead to misconceptions. But it's just so easy to teach it to the kids. So we need to remove stuff that's easy to teach and introduce stuff that is important in the long run. So then we need a theory. We need kind of some way of thinking about this long-term progression. And we found Vergniaud. Gerard Vergniaud. We actually went to his kind of castle in Paris. So he told us everything about his research. So he's a famous researcher that's been doing the same thing for, now he died a few years ago, but he's been doing the same thing for 30 years. And he actually told us, well, I keep writing the same thing over and over again. I will do it until somebody understands. So that's one way of doing research. So he has this theory of conceptual fields. I won't go into it a whole lot. It's based on Piaget ideas, let's say. He was Piaget's student. But a conceptual field is like, if you think of all of the mathematics, everything, it's like a big map, let's say, or you place it out on a big map. There will be some roads between concepts. So a conceptual field is like a city. So Mexico City would be like multiplicative structures, a lot of roads that's very tightly connected. So a big and important field, you know, and then it's the connection to some geometrical stuff will be, you know, maybe some highway to another city or whatever. So that's a good structure to think about a conceptual field. So we did with some conceptual fields. And he says he has a theory of representations and a lot. But something that we added is this concept of polysemy. Polysemy means, in our interpretation, conceptual polysemy. It means that there is this kind of super concept that you have several sub-concepts inside it. They are kind of feeds into this super concept, but they are not identical. So there are differences between, and fractions, and the whole quotient construct is the main big example. And you know, there are these lots of research about these sub-components of the fraction system, let's say. So this is something that we think is quite important, because a lot of the misconceptions we see, they happen between these sub-concepts. So you introduce, for example, division and fractions in very different ways, but they are supposed to work in the same way when you get to the symbol system. And that this will introduce certain stuff that works if you introduce fractions with like this pizza model, let's say. Some things that some invariants, some conclusions you can draw when you work with them will be wrong later. So they will have to be passed out or killed off. And this is all the same with almost every concept that you introduce. So therefore, it's quite important which ones you start with, because think about the student. I mean, every time you thought you learned something, and then you will have to relearn it or forget it. That's a very difficult thing, especially for the student that has more difficulties in school. So if we can, the more of this we can avoid, the better. So that sort of sets a bit of a standard for how to choose the early mathematics. So it must feed into the late mathematics in a particular way. And we think this, I mean, we talk a lot about symbol systems. We don't talk about abstract. We don't use the word abstract, because we use the word reasoning in symbol systems, so that you can understand the workings of the symbol systems and use them for reasoning without necessarily all the time thinking about some image or some situation that built up the symbol systems. But you can't teach the symbol systems in the beginning, because it's too hard. So that's why, the basic mathematics, let's say the number systems and the addition and multiplication, you can write it down in like 1 page in a book in algebra. So there are just 10 rules. So that's all. But it takes like 10 years to teach it. It's because you have to learn the symbol systems through in other ways, So this is kind of the underlying theory, and I will show some strange pictures here now, so you don't see much. But let's say in the upper row, so we have kind of some typical ways of teaching basic stuff. So we have multiplication as repeated addition, or we have this pizza fraction stuff, which is very easy to teach, and it works well for the earlier grades. But it introduces misconceptions, and from there it will be very difficult to move on. So instead, you should go to the later understanding that you want to have 10 years later, maybe. You analyze. How do you need to know multiplication, for example? Well, prime numbers, factorization, the distributive property, some things. And then you sort of invent some models, some thinking models or some ways of introducing that make these important things possible to do from day one with concrete material. So that's kind of the idea. and it's not so easy to make up these models, but you should try. I will show a little bit of it. So this is kind of our design theory, let's say, at least for the earlier grades. Or this, I mean, this is just another schematic of the same thing. You cannot take some, I talked about these super constructs or super concepts and sub-concepts. You know, you kind of have to analyze them, and then you create some models. That's a colored stuff there, and then you sort of use them to build up the simple system. But they should feed into the simple system without the misconceptions all the time. Okay, so now comes another theory. So that's kind of our basic design theory. So this is another theory to choose which kind of algebra to use. And there are many researchers, they all make their own kind of decomposition of algebra or early algebra. This is our decomposition. So some, for example, separate out the equality as a specific aspect of algebra. It's important, but I don't really like it. So we work with algebra as structure. So this is what we mostly do. So, and this is an early example. So this shows like a part-whole model built with cubes, or you know, you can draw it also, of course. So it shows. So why is this algebra? Well, this shows a general connection between addition and subtraction. Because here we have 6, or what do we have? Yeah, so 6 plus 2 is 8, 8 minus 2 is 6, and so on. So we have this additive family of numbers. But it's always going to be like that. So this is why it's an algebraic type of thinking. So it doesn't have anything. We never used anything about 8, 2, and 6. So it's going to be a general connection between addition and subtraction that you can use always. So this is kind of an early version of algebra structure. So the more of these you can find that shows general thinking, the better. And in the early grades, we kind of only do this. We hardly do any calculations, actually. So you see how we expressed it. It's this is actually done as a calculation, but this is not very common that we use this. Anyway, and then below we have algebra as operations on non-numerical symbols. So this is kind of the classic way. I don't need to say. So you introduce some representation of some unknown or some symbol. So we wanted to have that because that's so common in school. So we wanted that as a separate category. And then we have functional thinking. Functional thinking is not really algebra in itself, but it's usually involved in school algebra. It's sort of grouped together. It doesn't must be, but it. So that's like kind of functions. And you can start early. For example, I have a ball, and you have. I have 5 balls. You have some balls. Together we have 8 balls. That's like almost like a function. You can express it like that. And then geometric patterns, which is very popular, but I don't think they really lead so far. So this has been also quite popular in research on algebra. You work with these geometric patterns, but for me, they don't. I mean, it's fun. You practice your generalization, but it doesn't lead so much into the arithmetical structures, really. So now we should come to the content of the. Yeah, so we can take the next one. So as you hear, I'm mostly interested in these early grades, but it's Linda who does the later grades, or we do it together. So we have like 2 teaching models in this. One for the early grades. So that's built on, it's kind of what I talked about before, but in a simpler way, the TRR. And then we have for the other grades, from 4 and up, and actually upper secondary also. So I will start with that, so you can take the next one. So, yeah. So this is the 17th lesson in a sequence, and I will show how it looks for the students and teachers. So this was actually when we did this. We call it like a board, like a blackboard. So every lesson is based on one kind of a blackboard. It's just our name for how we introduce it. So this is the 17th board. And the students and the teachers said, oh, this was an easy one. So that was nice to have an easy one. But then they did it 17 times before. So we take the next. So I will go through this task. So the whole design is just the teacher just chose these 5 tasks, and then now you start work. And you see they look kind of difficult, I think, because this is even in the middle grade. So many will not be able to solve these tasks, and they work in groups almost always, in different kind of groups, and the teacher can decide the grouping. So we can take the next one. So we give this to the teacher. But we also give kind of solutions, or what we want to happen in the end. So this is like a quotient, or the multiplication of two fractions, or whatever you want to call it. And then we want, when the students work with this, we want them to come to the blackboard and present their work. And if you write an equality, they must have an argument like this. So you can't do anything without an argument. And interestingly, almost all arguments are themselves already established equalities of some type. So equality is really a generative concept. So you build new equalities on old known equalities. So here you start, with a cheap, rule for multiplying fractions. So we call it just a common fraction bar rule. And the commutative property, kind of reverse these. And then actually you could separate them again, really, into 2 fractions. And then you use the rule a divided by a equals 1. This is like something we teach even the 4th graders. So because 5 divided by 5 is 1, and so they easily believe this. It takes like 1 lesson for everybody. Then they identify this everywhere, regardless of the looks. So they can have like square roots and stuff that they don't know what it is. So they will still identify this way of looking at fractions, let's say, which is very powerful. It's the rule that solves all the other problems I showed before. That's not all. So we are not really interested in them solving this particular task. It's just a task we use to extract some new rule. So every task, or almost every task, or at least a set of tasks, will lead to a new basic rule that we sort of put up on the board. We might make it into plastic and pin it up on the wall, or write in the back of the books or whatever. Teachers do a little bit differently. And this is so that the students should feel that all work we are doing together in the class will lead to something that I can use later. So every task will be useful, even if I don't solve it myself. Because next time you will be able to use this rule about the inverse fractions. So this is this is the same type of reasoning as these blocks I showed you. Because we didn't use anything about square root of pi or 0.3. So we just used the sort of symmetry or structure of this. So therefore, even if we didn't do it with a and b, we could do the same thing with a and b, of course. So nobody will dispute this. So then and it's very powerful to have this rule. So we extract this rule. So, and this one. There's an alternative for some teachers want to do something simpler, so then they want maybe do the b thing, b to the 4. But this is the same, you see. Even if it looks kind of complicated, but it's a number divided by some number. So by the same number. So the same rule will apply. So now when they come to this, they can use a rule. And so on. I think I can move on. What do you think, Linda? To go through, or do you want me to go through all of them? Okay, I can do one more. Okay, so the next one. Because it took some extra time in the beginning. Oh, okay, this is important actually. So this is a kind of a fun task. It's fun because the best student, they will not solve it in the best way. And some weaker student always will actually solve it in a smarter way, namely this way. So then the good student, they get quite irritated that they didn't find a smart solution. And the smart solution is about the whole concept we use for equality. We use equality as replaceability. So two expressions or two whatever are equal if one can be replaced for the other everywhere in all their arithmetic expressions. So it's like a circular definition, but it's also like a recursive definition. So here, this is really to introduce this idea. So you have some equation to the right. The 3 to the power of 4 minus x is 72. And then in the other equation that you're supposed to solve, you have again 3 to the power of 4 minus x. But you already knew this was 72 from the other one. So you don't need to sort of solve for x in the first one. You can just take 3 to the power of 4 minus x and replace it with 72 because they were equal. Right? So this is a kind of smart way to think about equality. Yeah, and then we do that. So the next one. And this again is one of the ones that we had on the test, really. And you see again, it's the same, but actually it's a little bit more difficult when you have the numbers because you need to factorize the numbers to get this a divided by a. And if you look at the book, at least in Sweden, when you introduce simplifying fractions, you use some kind of circle, and you have some lines through the circle, and sometimes you can erase some lines, and sometimes you can put some new lines there, and you get different forms of the same fractions. But it doesn't really explain how to do this. So why can't you draw a circle with 36 parts and you color 23? Why can't you erase some of these lines to get some other fraction? It's impossible. It has to do with the factors. That's exactly. So this is the final answer. And it's a very easy answer, but because it goes back to very basic grounding principles for multiplicative reasoning, namely factorizing, which, as I will show, we, by the way, do the first lesson when we do multiplication. We start with prime numbers and factorization in grade 2. So you must know factorization, and then it's again a divided by a. So you create the 1. So if two fractions are equal, it's because they differ on a multiplicative 1. It's a multiplication by 1 in the form of a divided by a, or some a. So this, we have some 2's, 2 divided by 2, or 12 divided by 12. You can add it, take it away, because it's a 1. So 1 doesn't do anything to multiplication. So it's a general rule. Okay. So I think we go on. This is about the distributive property, so we can take. And in the end, and again, this is what you show the teachers. So their students has, in a way, to recreate this work, and some will maybe just work on one, the simpler one, if they found somebody. Some will maybe solve everybody. But the point is that you then have them go and present what they did so far, and you have a discussion. And you kind of want the teachers to come to this kind of conclusion on the whole lesson. So what conclusions did we actually draw from these tasks? Well, it was the one that we used this a divided by a. See, 1, and we have the inverse stuff with the fractions. It was something with the distributive property and this equality thing. We do this every time. This is what we do. So yeah. So next one. But so this is going to be like problem solving, because they have to usually think of ways of stuff that they don't know really, but they will be able to use some stuff that they do know from before. But you need some norms for this classroom to work. So now we come to the difficult thing for the teachers and the students in the beginning, because they will resist this, because it seems when you show this actually the first board, it's almost the same. So we don't start with simpler stuff. It's this difficult from the beginning. So then they will, I won't do this, So you have to talk about them. Well, this is Algebra Monday. Now it's going to be forever. It's going to be like this on Mondays. So you just have to accept it. But it's just one day. The other days you can do as you do normally. You work in the book and so. So we have to have some rules for this particular day, which has this name, Algebra Monday. It's good with a name, because then they can say, I love Algebra Monday, which they do also. Or I hate it, but it's just one day. So norms. So you should, as I said, there's no introduction on this lesson. You just give these 5 tasks, and the students, and then you can go around and help them a little bit, if they can't do anything. But they start with something in groups. As I said, all calculations or all reasoning, every equality you write should be explained. So you couldn't really do what the other kid did, because he couldn't, of course, not explain this, not in a mathematically sound way. So you would have to sort of go through it from the beginning with his kid, so that he could get some established rules he could refer to. And students are not really corrected by the teacher in that sense. They are supposed to explain to the other students. So the other students understands, or not, maybe. So that comes on the other board. Maybe you don't understand, but that doesn't matter, because we will do it again and again and again. So you don't need. So that's a rule also. We can take that next one. So no hands. So the teacher decides who's to say something. So the teachers kind of, and the teachers, they are very creative. They invent different systems to handle this. So some, for example, if you have shy students, or if they are afraid of showing mistakes or stuff, you can have them work on like big whiteboards that are like this big in their groups, and then they can just go and put the blackboard up or the whiteboard up. So then they don't need to sort of stand there themselves. So the teachers invent a lot of small tricks, because it's quite hard to get the group of students to sort of work in this way. And this is very good we have collegial meetings, I will show. So we can collect a lot of these tricks in these teacher groups. So somebody invents, so you must love mistakes. So you must teach your students to love mistakes. When I was visiting Linda when she was teaching in prison, that was the first thing her students said. She loves mistakes, and it's true. So you actually want the students to do a lot of mistakes, because from the mistakes we can learn. So and this is the same from grade 1 actually. So you must have this. And then it's this is kind of interesting also. It's completely normal to not understand. So as Linda says, if I would give you tasks that you can solve, I'm not doing my job. You're supposed to not be able to solve it, and maybe by trying really hard and working with others or looking at others, you solve it, maybe, or not. Or maybe some of your colleagues or your student friends present something you don't understand. They try to convince you, but you still don't understand. Okay. Yeah. Yeah. So she said that every week there's also one kind of simpler task that everybody can start with. So you just don't, yeah. So everybody needs to be able to do something. Okay, so the next one. So this very simple idea, it creates 3 things. So it creates a repetition structure, because we can do the same thing many times, as often we like. So, and you don't want to do it many times in a row, because if you want somebody to remember something so they can recall it, you should first make them forget it, and then recall it with minimal help or maximum effort. So this is from cognitive science. It's a very basic thing. So you make some, everybody understands something or learns something each lesson, and then they can't do it really exactly the next lesson, only a little bit later. So and this way of having these 5 tasks is very easy to create these repetition structures. And then there is this motivation structure. So this is very difficult. I mean, of course, the student will. They will remember that, they got scared. They actually get scared. And then after a while, they will kind of, okay, now I can solve this. After maybe some weeks, they will very much realize that, I learned something. Now I can do it. And this is very motivating. So you can't have students do a lot of easy stuff that they already know and think that is motivating. It's not motivating. And it's not motivating to not feel that you're learning. So you must really understand yourself that you're learning. You must notice you're learning. So that's one reason it's good to do very difficult tasks like this that you eventually know. And as you saw, this was the board 17. We sort of introduce some old stuff now and then just to get this motivation structure working. And the teachers can also, after, I mean, it's kind of fun because after like 12 times when they did it, so we are happy that our pilot teachers that I will talk about in a moment, they have to do this 20 times before they can be facilitators. And we could have chosen 10 times, but it's too little. So something starts happening after like 12. And then the teachers see the structure. They kind of, oh, now I understand. Before, even though we had those explanations, they kind of, oh, there's a lot of random stuff here. But after a while, they say, okay, now I can myself start to kind of replace a little bit. Because even the same, the motivation in the class as a whole, and teachers are extremely good to sort of sense the motivation in their class. It's just that when they do their normal teaching, we do have a lot of textbook work. You can't really do anything about it. But what should you do? You can do some fun stuff, but it doesn't really work. But here you can push the whole class, till they almost break, and then you introduce something simpler the next week. So when they get this kind of, and this can be different in different classes, even for the same teacher. So it's like a wave through the class. So when the teachers, once they sort of crack the code of how to work with this motivation in the class, this is very advantageous for them. And then we call it kind of like a safety structure, because in the typical lessons, I mean, some they will sit there and do nothing actually, especially in grade 8, they do absolutely nothing. But still, most they feel kind of safe because they work with tasks that they can. I mean, you come to a page in the book and it's an example of how to solve the task, and you can kind of solve most of the tasks, and you sit there and do that. And maybe you ask the teacher for help. So that's a typical Swedish lesson. So this is kind of, in a way, kind of high within lesson safety. You can feel safe that I know how the lessons are going to work. We kind of want to, we also want them to feel safe in the lessons, but not because they can solve the tasks, but because it's okay to not understand or to make errors. So a different kind of safety. But in the long run, so this is even more important, in the long run, in the typical teaching, as I explained with these misconception things, I mean, you will all the time, it works fine in one lesson, but then suddenly, nothing works anymore. So your legs are kicked away from under you all the time, every other week or something like that. So then after a while you start feeling, well, mathematics is a very insecure type of environment, because I feel like it works for me, but I don't learn. I don't learn in a way, so it becomes easier and easier. So we want mathematics to become easier and easier, the harder the math gets, let's say, because you sort of crack the code for this algebraic reasoning. So it should become, so you should feel that you learn something that is useful. So these three structures kind of go together. Okay, the next one. Okay, so I will need to go through this, maybe jump through a few. But I will show you kind of, we have a different structure for these first grades. Because we tried these 5, it works also. But we can't do that only. Because we need to build a firmer, more complex basic structure. Because we don't have the simple system reasoning already. So we can't use that. So we must build on other stuff. So next one. So this is like the first lesson. It could be for 6-year-olds on equality. The actual first time you show the equal sign. So next. Okay, this is in Swedish. I will say what it says. So we give the teachers, we talk to the teachers, kind of give them this PowerPoint stuff. So here is the basic plan for this lesson. Might be like 7 PowerPoints. They shouldn't show this to the kids. So this is just for them to plan the lesson. So it is the rabbit and the fox, let's say. So the rabbit says, I collected 3 carrots today and 2 yesterday. And the fox says, so we have these actual animals. It's very good with little stories. We don't like reality. We only use stories because anything can happen, but it's still, it's much easier. And we actually compared. So it's better to use the stories and these animals and stuff. So the fox, I collected 4 carrots today and 1 yesterday. Oh, then we have as many carrots, says the rabbit. And this is the teacher sort of telling this little story to the kids. Yeah, so the teacher says then, oh, or the fox, no, that can't be right. 1 and 4, or 1 plus 4, isn't the same as 2 plus 3. And it isn't, you know, actually it isn't. It's equal, but it's not exactly the same. So you use equality to say that different things are equal. That's what you use it for. So the teacher, can you help the fox and the rabbit to show? And then they, you know, you have a little discussion, and we can take the next one. So we use these multi-link cubes, colored cubes. So we cannot build this practically. Oh, how many did the fox have today? How many did the rabbit have? How many did they have yesterday? So we build it. So the pupils can build this themselves in pairs, maybe. Next one. And then we have this. We have this actual plus on a piece of paper. So they get the plus and the equal. So this is the first symbolic thing they do actually, or they did some with patterns before. Okay, so you build this. So you say, well, this is equal now, but how can we sort of can show if you build the 2 plus 1 or the 4 plus 1 and 2 plus 3, they are as high or as many and stuff, but we don't want that to be the definition. We don't want you to say 4 plus 1 is equals to 2 plus 3 because both are 5. Because if you think of an equation or something, you can't really know what the sides are. This is not a very bad way to think about equality, that they are as many or as big or as long as whatever. So you must have a rule. I mean, normally in equality, you have to manipulate one of the sides to become the other side. Then you have showed it without referring to the sum or whatever it is. So the next one. So we show, okay, but let's take a 1 from the 2 and place it on the 3. You see what I do with the words? So it's because in the words and in the symbol 2, the numerical symbol, there's no 1 in the 2, you know, because it's just a curly thing. There's no, you know, straight thing in it, and not in the word either. So, but in the practical cubes, there are, of course, if you have the 2 bar, there will be 1 in it. So this is how we kind of move from actual handling of concrete stuff and slowly sort of build an understanding for what would this mean in the symbol system. So we want in the head, in the beginning, we want this 2 to kind of, oh, I can think of the 2 things. So then I can take 1 out, but they write the 2. And we actually work a lot with this kind of arrow systems and stuff. It's a schematic representation that kind of is the same then when you work with the concrete stuff as the symbolic stuff. So this is a way. And then, of course, if we take the next one, or, okay, well, then you kind of, okay, except for the colors, you kind of rebuild the 2 plus 3 into the 4 plus 1. And then it's equal because it's the same. It's not only equal, it's actually the same except for colors. So then maybe you show some other to the students, work a little bit more, and then you give them some work. So then you say, okay, now you show some equalities yourself in pairs, maybe. And you just pick one. So this is kind of similar. Pick one of these. And for some, they will take the easy one. They will actually use the cubes and make the drawings on the paper and stuff, because they need to. But some will attack the last one already if they are 6-year-old. But they are still doing the same task, but with different numbers. So then the end of the lesson is that the teacher goes around, checks a little bit, and asks somebody to present and discuss. But this is a powerful thing, because what you have to understand about lessons is that you will have a huge variety of students all the time, not only 6-year-olds. It becomes worse. So the difference between the sort of the one that learns the slowest and the fastest will be bigger and bigger. So every lesson must be so that everybody can participate. But then you have to have some kind of easy stuff, but you can't, keep them doing easy stuff only. But to be in an environment where somebody is doing the more hard stuff on the same problem, I see it as the same problem, then you will grow. So everybody grows, and still the good ones, they can have something really challenging. So this is the basic idea in this. So all lessons are kind of like that. So the next one. Okay. So it's a little point. Yeah, I will. So I will just show the. Yeah. So I can take. Can I go through, because it took a little bit longer time here. Yeah, we go to the. No, go further. Yeah, I started a little bit later, but anyway, we can go through. So I mean, we can take this one, for example. This is about multiplicative structures. So the one up on the right, this is the first lesson on multiplication. So you give them some multi-link blocks, different numbers to every student or every pair, and you ask, build rectangles from these blocks. And this is actually factorizing the numbers. So which kind of rectangles? Because we kind of define multiplication as the name of a particular rectangle with a certain number of columns and a certain number of rows. And we build the lesson in more or less the same way as I showed you on this. And we go on to do a lot of other advanced stuff. But you can get this presentation, you can look at this if you're interested. So I need to go. Yeah, let's just go on. Okay, so I will have to talk about this one. So how do we do this in practice? So now I move on. So I passed by the content. So in practice, Linda and me, we develop these lessons every week. And then we meet with the teachers in each municipality. At first with these pilot teachers, we recruit pilot teachers. Different in many depending on the size or the scale, what they want to do with the scaling. And we show them pretty much what you saw. And then they report how it went last week. So that's the collaborative structure. So, so we of course have to then meet all these teachers, every day for 2 hours. So it's a lot of work for us. So it's a very intensive contact with the teachers, and we get feedback on everything right away the next week. So this is one of the reasons it can't scale too much. And even we will run into problems even within a municipality. But this is why we have this pilot teacher facilitator structure. So if you take the next slide. So after a while, after like 20 weeks or maybe a little bit more in practice, you start to scale this up to other teachers. And then the facilitators can lead this, perhaps with some assistance. So we sort of teach them to lead these kind of sessions. And then the first 20 lessons they already did themselves. So they've been through all the problems, yeah, so we can take the next one also. And this is kind of hard then, because, there's a lot of decisions to be taken. Because, for example, the municipality must make teachers free 1 particular or 2 hours. When we scale it up, they must have 2 hours that all teachers in the whole municipality, 100 or maybe several hundred teachers, should be free at a particular time. Very difficult arrangement to make. But you have to do it. And sometimes it doesn't work, so we have to work around it a little bit. So every municipality gets a little bit of their own design in the end. But this is the thing. You start working with the leaders, then you move on to sort of get some pilot teachers recruited. Then all these arrows is that we work with them 20 weeks. And then we sort of go on, we scale it up. So this is like a schematic picture. And there's some testing and stuff going on here. So yeah, but for example, this getting all teachers free a particular time. That's for some municipalities, even if they have like powerful leaders, they just can't do it. So I will go to the conclusions. Yeah, they come here. Perfect. So I will only have 5 minutes, and then I ask for 10 minutes more because for some questions or whatever. So Yeah, so the next one. So what did we conclude so far? Well, we like this idea. So we were asked, why don't you have a lot of PhD students or some other facilitators that can work with us? It's because we want to build this competence in the municipality. So we want project leaders that can, and these pilot teachers, because they become very good. They are good from the beginning, but we strengthen them even more. So we recruit the best teachers, and then they become even better. So it's very good for municipalities to have like 20 super excellent teachers, because they can do a lot of other stuff later. So this is an advantage. So we build local competence, both related to Algebra Monday and to other stuff, and also this leadership competence. So they can hold these meetings, and the municipality eventually, they will have to learn to organize this whole thing themselves, more or less. So this is building local competence. And it's kind of, it's still relatively flexible, we can say. So we have a few variants of these arrangements, because if they can't really make everybody free, we can do it in some other way. And this is also important. This is a coherent algebra approach throughout the system. So these teachers will actually meet even from grade 1 to grade 9 and discuss. And they know exactly what happened before. So now it's new, but in a few years, they will know what these students been through. This is very important, I think, because now they know nothing about what happened before. No, absolutely nothing. And it's kind of easy to make the teachers enthusiastic, because because they have been hearing so much about problem solving and all these different things for years, and they don't feel it helps their teaching. But they know that when we show this, do your students make these errors? Yes, they do. So okay, we will buy into it. So it's pretty easy. So it's complicated in some ways, but still pretty easy. Okay, next. So downsides, it's limited scaling, because we don't want to do more municipalities. We can't do more now, but even if afterwards we might not want to continue. So due to the extensive researcher-teacher contact, so then you could think of like Susanne Prediger and this Quamaths. They're doing a huge thing. Yeah, it's in the bottom. They are educating facilitators, like several hundreds of them, that are like teacher educators. But I know, because I talked to her, it's not working very well. It's very difficult to get them to not sort of twist the stuff a little bit. So I don't know. And some municipalities might not even be capable. So we don't know. The next one. But we are thinking of some inter-municipality thing. So you can kind of educate your pilot teachers in another municipality, or perhaps a little bit by us together, and they go to sort of practice in another municipality where it already works. That's one way. Could be scalable. And maybe we should have more material components than we have now. I don't know. It was very difficult with TRR, but maybe. Or some cross-municipality, leadership work. But that's kind of in the planning stage. And of course, the surrounding municipalities, they will kind of be very curious. So they are already trying to buy into this, if you have one municipality. Okay, the last one. So generally then. So this is, I think, the most important math you can do. So it's relatively easy to sell it and have the municipality invest a lot. But let's say you want to work with symmetry in geometry. You can't really expect this kind of organization. So what you want to do will affect what kind of collaboration you will be able to do. So simpler, more remote stuff will be much more difficult. So you're going to have to design differently. If you're going to do not as, big stuff as this. And I think also this will lead to that different kind of innovations will have to have a different balance between this sort of personnel multiplier strategy and the material strategy and so on. So maybe you have to do, if you want to do more remote math, let's say, maybe you want to have a simpler design with less disruption to the teachers, to their routines, because you can't require as much energy from the system. Yeah, so this was it. some difficulties, but still. So maybe some questions, and or you just want coffee.
Maybe I can use that one.
Okay.
And,
thank you, Ula, for your talk, and I'm going to try to explain me because my English is not very well, but I'm going to try. I'm trying to connect the first part of your talk and the last part when you talk about the teachers and the problems, the misconceptions of students. So I wonder if teachers were trained about those problems.
No.
My question is, what was the training for the teachers, for the pilot
Yeah.
teachers, and how much teachers integrate the pilot teachers group?
So the question was first, do we do some training before? No, we don't do any training. So the pilot teachers will be quite good because we choose them as good. And the misconceptions, they are actually, I mean, teachers know about the misconceptions. So they are that's something because they see it every day. So and we don't so much need to teach them about the misconceptions. We need to teach them about the smarter way of teaching the students to reason. And then they just try it, and we show them for every week. We kind of show them, okay, here are 5 tasks. Here are some interesting ways of reasoning about these tasks, and now go and do it. And then they learn from the students. So there's no special education for them.
No education, but training about the misconceptions. The slides that you showed to us.
Yeah, we show them to them.
Okay.
We
okay.
So every week there's a 5 new.
So then the teachers convey to the classroom that problems.
Yeah.
And then come back to share their experiences.
Yes.
And in what time incorporate the other group of teachers?
Yeah, so when they did 20 of this, so 20 boards with 5 questions each,
Okay.
after 20 weeks or whatever, it usually takes like 30 weeks because there are some breaks or whatever. Then then they can be facilitators or advisors for another group of teachers. So then they maybe work with 5 new teachers. And then they start from the beginning with these teachers.
And I would like to know if you are working in a special assessing about on the project more than the teacher experiences.
This would be quite interesting to do that sort of research if we would kind of record our sessions with the teachers. But we just do that as a development thing. We don't do that research at least not now. So it would be very rich and interesting research that could be done on these teacher sessions. But we don't do that.
And my last question is, what was the principal challenge did you face in this project?
The hardest thing is organizing the municipalities, for sure. And Sweden is we're not very authoritative system, so it's very difficult to make decisions from above that's supposed to go through the whole system. So, but something that's not so hard is because we work with all sorts of schools, and Sweden is kind of segregated actually. So, it's not more difficult to do this in the very difficult schools, but even if in grade 1 or 2, what you notice is that there is more other activities going on. I mean, there's more like fighting, so they have to kind of cancel a lesson, and there's more canceled lessons. So there is a kind of, you can see the segregation between the schools in that But even if you have, I mean, we have schools where there's not one single student that speaks Swedish as a first language, but that doesn't really matter so much. It works similar.
Do you have some paper to share with us about
This
that
is kind of
project?
new, but do we have some? We are actually writing a paper in this conference, so we can give it in a few weeks. I don't know.
Okay.
Yeah, so this is kind of new because the first pilot teachers where we started, it's just less than 1 year ago. So now we have 5 municipalities, so it's really fresh in that sense. So we came kind of a long way fast because we want to kind of develop it first with the municipalities before we do a lot of research ourselves. So we are more like developers, maybe.
Okay. Thank you for your project. It's interesting.
Thank you.
Congratulations.
We are kind of running out of time, but maybe someone wants. Ula, can we share your slides?
Yeah.
Webpage?
And there's if you're interested in particularly the early math, there's some kind of stuff that I never actually saw anybody else do.
I'll upload them in the webpage. Anyone who wants to? Yes, Peter.
Yeah, so you're doing everything you can to avoid misconceptions on Mondays, and then the students can learn misconceptions Tuesday through Friday. Yeah. What do you think about that?
It was just a choice to make it simpler, but actually it spreads over to the other lessons, and in the early grades it spreads a lot. So they actually can, I mean, they do this. Some do this all days. Just some never even since they started they never use their textbook anymore. So they just choose to convert completely. But from grade 4 and so on, and especially from grade 7, they say it spreads a little bit still to the other lessons. So, and the teachers, of course, realize a lot of things. But it's kind of becomes strange if you have a chapter in your book with fraction, with all these pizza models, and then you have to tell them something else. So then it can happen that the teacher say, okay, we just skip this. We skip some stuff it's already handled by Algebra Monday. And there's a lot of spread between kids in the same, because some have teachers doing this already and some don't. And when they are, playing football and stuff, it kind of, the rumor spreads among the kids actually. So that's kind of fun.
And Ola, you had the graph with different questions of different difficulty.
Yeah.
And you said that your goal was that they would all be the same.
Yeah.
Do you have any data on that?
No, not yet. So, but this, I mean, our test is kind of designed to be able to detect that sort of thing.
Thank you.
So a quick one before leaving. Otherwise, please let's give a round of applause to Ula. Thank you, Ula. I have an announcements. Coffee break. There is coffee.